Oh, what a beautiful day. Not one cloud in the blue sky. And there is the sun, source of all life on earth, bringing light and warmth. But it also has a darker side, radiating harmful ultraviolet light. Hello everyone, and welcome to our 10th exciting STEAM project. In this special video, we're setting aside our microcar to guide you through building your very own Sustainable Development Goals solution project. We'll be using the BBC Microbit and the block coding environment of Microsoft MakeCode. We're starting with a simple yet impactful project, embedding an ultraviolet sensor that will alert you when UV levels become too high. This project serves as a starting point for a brand new series of SDG-focused solution projects specifically designed for STEAM teachers who are just beginning their journey. In fact, we are assuming that you don't have any prior experience with programming, sensors, or actuators. We call this foundational level the Scout level. My name is Peter. I am the founder of EdukoMondo, as well as a certified STEAM instructor and course developer. So today we are going to talk about ultraviolet light. But why do we even bother? UV radiation harms people by damaging skin cells, increasing the risk of skin cancers and premature aging. It can also cause eye damage, like cataracts. This chart shows the geographical variations in UV intensity. The closer you live near the equator, the higher the UV index. The UV index is a number between 0 and 11, where 0 is no danger, but 11 is extremely dangerous. The good news is that you can do something to mitigate the harmful effects. Once the UV index is higher than 2, you have to apply a sunscreen, wear a hat, or look for a place in the shadow. The higher the UV index, the more intense the UV radiation is, and the higher the protection of your sunscreen has to be. In those cases, it is important not to stay too long in the sun, but seek protection in a shady place. In other words, this project directly contributes to SDG3 for good health and well-being by addressing the direct impact of UV radiation on human health, but also SDG4 quality education by providing STEAM learning opportunities. And it also contributes to SDG13 climate action through enhanced atmospheric understanding and environmental awareness. So the goal of today is that we will read the UV radiation intensity as an analog signal using the BBC Microbit and a UV sensor. We will convert this reading to the standard UV index numbering system. That UV index will be displayed on an OLED screen, but we will also include some warnings when we reach the higher UV intensity levels. Not just warnings, but we will also provide some sun safety recommendations. And in addition, we will also offer visual feedback using a green, yellow, and a red LED. Let's start by reviewing the necessary components we will need for this project. We will need, of course, first of all, the BBC microbit. We are using version 2, and the USB connection cable because we are using a Windows machine. A breadboard with 400 or 800 holes. A microbit breakout board. I prefer this one because it can be mounted on the breadboard and it has this very handy I2C slot. The UV sensor. We are using the sensor with reference UVW30A, which is broadly available and is also a very cost-efficient sensor, ideal for projects like this. We have the OLED display. We also include a green, orange and red LED. And for those LEDs, we also need 3 resistors of 220 ohm. Because we want to take the project outside, so disconnected from any computer, we also need an external power supply of not more than 5 volt. The one that I am using is a very simple 3 volt based power supply based on 2 AA batteries. And we also need some jumper wires, and trust me, you will never have enough of these. So let's put all of this together. The first thing is we take our breadboard and we simply click the expansion board right on top. Next, we'll mount our 3 LEDs, and notice that an LED has a short leg and a long leg. We are placing the short legs into the common negative rail, which is also sometimes referred to as the ground rail on our breadboard. Once these 3 are installed, we'll take the 3 resistors, and each resistor gets connected to the longer leg of an LED. Make sure to bridge that small gap running down the middle of the breadboard with these connections. Once that is done, we connect the UV sensor, and the UV sensor has 3 output pins. The one marked with a plus sign goes to one of the 3.3 volt pins on our microbit. The one marked with a minus sign goes to one of the ground pins. You will often see me use a red wire for positive connections and a black wire or a darker wire for the ground. This is a standard practice in electronic wiring. And finally, the pin labeled out carries the analog signal that we want to capture. So we will connect that to, for instance, pin 0 on the microbit. Next, we connect our LEDs to the microbit. The green LED gets connected to pin 6, for instance, using a green wire. The orange LED goes to pin 7 with an orange wire. And finally, the red LED connects to pin 8 with a red wire. One of the nice things about this expansion board is that we can use either these holes on the breadboard or the pins directly on the breakout board. For the finishing touch, we'll add our OLED display by simply plugging it into the I2C connector on the expansion board. That's it for the physical build. I know everybody is now ready to jump into the programming part, but first we need to understand just a bit better the working of the ultraviolet sensor. To understand the functioning of a sensor, actually any sensor, your first port of call is the datasheet. All electronic components have a datasheet issued by the manufacturer. Search for UVM30A on the internet and download one of the many datasheets that will pop up. From the datasheet, we extract the information that we need for our project. Specifically, this graph is of interest. It shows a couple of things. First of all, it shows that the UV sensor has a maximum output of around 1200 millivolt or 1.2 volt. It also shows that that maximum of 1.2 volt corresponds with the maximum UV index level, which is 11. And you also see that the relation between output voltage and UV index is quite linear. That is very important information for our map function, mapping the readings of the sensor to the UV index scale. On the datasheets, you will also find often a reference chart that shows the intermediate values. And this last overview is quite handy to craft the recommendations. Recommendations that go from no protection required to protection required to actually the extra protection. And now, finally, you can start coding. And here we are in our live environment. You know how to do it. We need to create a new project and we give it a meaningful name, for instance, SDG3 UV alert. I hit the create button and we are in our blank canvas. The first thing I want to do is to initiate the OLED. Why? Because we need an extension to make that work, and I go to extensions. I need to find it, so I type OLED 12864, hit the magnifying glass, and this is the one that I want to install. Once the extension is in your list here, I can click on it and I need to initialize it in the on start block. As you remember from the previous lessons, because we are using this OLED, there might be a conflict with the 5x5 LED display on the microbit. So I will disable that, and I do it by going into LED, more, and select this function, LED enable false. In that way, we will probably not run into issues with the LEDs and the OLED. Good. The next thing is that we need to populate the forever block, because that is going to capture the analog readings from the sensor and map it to the UV index scale. And that is also the reason why I asked you to remember the maximum output voltage of the sensor. Indeed, it is 1.2 volt and not the 3.3 volt as you may perhaps expect. This also means that we will never get to the 1023 as the maximum analog read value. But what is then the maximum analog value that we can reach with this sensor? Well, we can calculate it by dividing the 1.2 volts by 3.3 and multiplied that number with 1023. The result is 372. And now we have our new maximum read value. First, we create a new variable. So I click on variables, make a variable. I give it once again a meaningful name. That's good programming practice to give your variables a meaningful name, because that will help you and others to better understand your program even after many years. So let's call it UV_index. In the forever block, as I said, we will capture it, but we need to further refine what we really want to do there. So I'm going to capture it by dragging the set function to the forever block. And because I don't want any decimals as an output, I go to math and I select round. And I replace the 0 with this new function. And now I can insert my map function, which I find under pins, and I replace the 0 with this particular function, with this map function. And I now have all my variables. I can populate it with the correct numbers. So, first of all, this is going to be an analog read from pin number 0. So I go to pins, take the analog read and move it here. That analog read, as we have just defined, is not between 0 and 1023, but between 0 and 372. And the low is 0, and the high is going to be my highest index on the UV scale, which is 11. So that's it for capturing the analog read from our sensor. Of course, now I want to show that on our OLED. So I go to OLED, and the first thing that I want to do is I want to show a text, a string at the first line, and my text is going to be UV level or UV index. Maybe that's better. UV index. That's correct. And underneath it, I'm going to show that number. And that number is going to be displayed one line below. So the Y value has to be put to 1. And the variable, the number here, has to be my analog read from pin number 0. Is that correct? No, I'm making a mistake here. What I want here is not the analog read, but I want my variable UV input. So I have to go to variables and change this number into the UV index, because I want the UV index, which is the output of my map. I don't want the analog read there. I end with a short pause, and because I don't need to do like every millisecond a reading, I can set this pause to, let's say, 5 seconds. And then I will clear my OLED display so that it's ready for the next measurement. Now we will work on the warning messages. And for this, I will make a distinction between the messages on the OLED display and the LEDs that we have on our breadboard. So let me first create a new forever block. And here I will need to add a logic function. So in my logic list, I just go for the if statement. And here I want to have actually just one if statement that is going to check the UV input and will compare it with a particular index number. And then depending on what the relationship is, whether it's lower or higher, it will display a particular warning on the OLED. So if, and this one will be replaced by another logic block, which is a comparison. And the first variable is my variable UV index. If that UV index is larger than 2, then I want to show something on the display. So I have to go again towards a string. I want to show a string. And don't forget that in our previous block we already are at the Y position 1. So here the Y position will be 1 below again, so that's going to be 2. And the text is going to be warning. So when the UV index is higher than 2, an additional line of text is going to appear on the OLED that says warning. Now, because I want to do more than just giving a warning, and I want to end it even with an exclamation mark, I'm going to add also a recommendation. So I'm going to add another text, and this time the Y will be 3, and that's actually going to bring us to the bottom of our OLED, and we don't have that much space to write something, so I'm going to keep it very simple by saying sun protect. Maybe the on will also work, we will see. Sun protect on is going to be the message that you will get when you are higher than the UV index of 2. Once again, I will pause with a 5-second delay. 5 seconds. And I will clear the OLED display so that it's ready for the next reading. And it will clear the display completely if that reading is going to be different. So for instance, if the reading will drop to 1 or 0 again, I don't want sun protect and warning text to stay on the OLED. I want to clear it from the OLED display. The next new forever block will be to control the 3 LEDs. So we know that the green LED is connected to pin 6, and we want to switch the green LED on if the UV level is smaller than or equal to 2. So to do that, I'm once again going to include the logic block, and once again I want to compare two values. The first value is my variable UV index, and the value that it has to compare to is 2, and as I said, it has to be smaller than or equal to 2. Then the green LED should light up. Switching the LED on is triggered through a digital write command, and those commands are under pins. Digital write pin, and as we just said, this is pin number 6, and I put it to 1. Basically, I need to do the same for the other reading. So I have 3 pins. The next if statement is going to be slightly different. Nevertheless, I'm going to copy paste the previous one. Make sure that you place the next if statement underneath the if statement that we have, so at the same level, not embedded. So it's very easy to put it here, but then it's not correct. It has to be really below the previous if statement. So the next if statement is going to check whether the reading is between 2 and 8, and then it's going to switch on the orange LED. So I need to compare 2 variables. So I'm going to replace the one that we already had there with a Boolean, and now I can replace it here and do some copy paste with the other variables. So the UV index has to be larger than 2, but it has to be smaller than or equal to 8. And then I have to put my pin number 7 to 1. And then the last statement, so once again, copy-paste. I'm going to move it here and make some space. The next one, if the UV index is larger than 8, larger than or equal to 8, and in this case I better change it to smaller than 8, so then it will go up to 7, and once it is higher than 8 or higher than 8, then I will have my digital right pin number 8. I have to activate my pin 8 to 1. Theoretically, this will work. However, if the green LED is on, because the reading is below 2, and then I will go into an area with an increased UV radiation, and the yellow LED will light up, you will see that also the green one will continue to burn also. And to avoid that, I need to add all the pins that I use for the LEDs and set the digital right to 0 for those LEDs that should not light up given a certain UV level. So let me do that first. So I'm going to control copy paste. And here pin number 7, pin number 8 have to be put to 0. And that should make our project work flawlessly. I would say download the code, unplug the BBC microbit, connect it to the external power supply, and go outside to make some measurements. Here we are in the outside, and unfortunately, because the text on the OLED display is difficult to capture on video, you really have to believe me. But you can see very well how the green and the yellow LEDs switch on or off depending whether I measure a UV index of 0 or 1 of 3 or 4. That's it for this project. Let's go back to our classroom and ask your students what other ideas they may have to make this solution even more useful. Let their creativity come up with new and innovative ideas. Next to the visible warnings, you could, for instance, include an audible warning. This is useful for people who have reduced eyesight. For instance, a happy tone will indicate a low ultraviolet level, while a high-pitched alarm will sound if there is a high level of ultraviolet radiation. You can replace the 3 LEDs with one RGB LED. That will require some rewrite of the code using analog write commands. Let your students' creativity go wild, mixing paints according to the color wheel. Or let them create a colorful box to host a project and position that box somewhere on the playground so that other students and teachers can check the UV index and take appropriate action. And of course, this is a very good starting point to dig deeper into other aspects of SDG3 and SDG13. That's it for project number 10, where we built a solution that offers an answer to one of the challenges in SDG3 on personal health and safety. I hope you liked it, because I certainly did. In our next series, we will build more SDG solutions aimed at kindling the innovative mindset of students and teachers alike, while they learn and teach about math, science, engineering, technology, and art. See you in the next lesson, and bye-bye for now.